Good afternoon. In this lesson, we want to introduce the concept of the inverse linear application. What is the statement of the problem? We have a linear application between the spaces Rn onto Rn. N-dimensional, the first space has dimension n, the second space has dimension m. Now, we have defined the concept of injectiveness. I remind this concept. N is called injective if for any vector W belonging to the second space Rm, the equation n of x belonging to Rn equal W as always as no more than one solution. This is the concept of injectiveness. Let's do the following consideration. What is a necessary condition for a linear application to be injective? Let's do this example. And from R4 onto R3, a linear application from a first space having dimension greater than the dimension of the second space can never be injective. A simple analysis of Shea-Capelli's theorem, a simple analysis based on the Shea-Capelli's theorem shows this property. Why? Because the associated matrix will be a matrix having 3 rows and 4 columns. The matrix will be 3 times 4. There is the exchange. 3 times 4 means 3 rows and 4 columns. Okay. This is the matrix associated to this linear application. The kernel of this linear application is, we already know what the kernel is, how the kernel can be obtained, can be computed. We solve the linear system L times a vector belonging to R4 that is having 4 components, x1, x2, x3, x4. First element times first element plus second element times second element plus third element times third element plus fourth element times fourth element. This matrix is 3 times 4 times 4 rows times 1 column. Since these 2 indices are equal, the product is consistent. Equal 0, 0, 0. Equal the null vector of the second space 3, 0, the dimensional null vector. Well, but the rank of this system can assume as highest value the value the rank 3. This matrix can be maximum of rank 3 because the rank 4 is not possible. The fourth row is not the matrix has not the fourth row. Well, but the solutions of this system are then infinite to 4 unknowns minus rank 3 or rank 2, rank 1. Anyway, I want to convince you that the solutions will be always infinitely many solutions. The solution can never be unique in this case. But since the solutions are the vectors of the kernel, if the solutions are infinitely many, this means that the kernel of L will have null vector, comma, V1 not equal to the null vector, V2 not equal to the null vector, and so on. Since the kernel, we remember the theorem stating a linear application is injective if and only if the kernel consists of the null vector only, and then we can conclude then that this linear application can never be injective because the system has always finitely many solutions, and then we have infinitely many vectors with the kernel, not only the null vector. And then this linear application can never be injective. Why? The reason is that the first mention, the reason is that the highest possible rank of the matrix is less than the unknown. What is the highest possible rank of the matrix? It's 3, like the dimension of the second space. What is the number of the unknown? It's the dimension 4 of the first space. If the highest possible rank is always less than, the number of unknowns, 3 or 2 or 1, then the system can never have unique solution. And then we can say that a linear application, for a linear application who can be injective, the dimensions must be the second dimension m greater or equal to n. If x, the first dimension, is greater than the second dimension, we always have a matrix having the highest possible rank less than the number of the unknowns. And then the system will have infinitely many solutions, the kernel will have infinitely many vectors, and then L is not injective. For the matrix to can be, that is, if L is injective, it follows that the basis, the necessary condition of the basis is the second dimension is greater or equal to the first dimension. This linear application can never be injective. Well, now I cancel this analysis based on the Shea-Kapelowski theorem. No, first of all, I cancel here, but not all. Just a moment, I will write this inequality better. I write a theorem if you want, an implication. And injective implies M greater than or equal to M. Well, now I cancel this analysis. And here I cancel injective, and sorry, here I get more code. Injective is for any vector W. The equation has no more than one solution. The solution is X, the vector X, belonging to the first space. This is the complete definition of the injectiveness. Now, I cancel injective. I cancel here the definition. And I give you the definition of surjectiveness. A linear application is called surjective if for any vector W belonging to the second space, the equation L of X equal W has at least one solution. X belonging to R and the first space. Let's analyze L injective, L surjective. Sorry, for the moment I cancel this theorem written in this way. I write it in another way. In the previous analysis, we have proved that L from R4 into R3. We have said by analyzing the matrix, the associated matrix, the corresponding system, and by considering the Shakespeare's theorem, we have said that this linear application, that is, if M, the second space, the dimension of the second space is less than or equal to N, it follows that L is not injective. Okay? The result of our previous analysis is this one. But as we know in logic, if we exchange, if we invert tests and hypotheses with the opposite properties, then L is, what is the contrary of L is non-injective? The contrary or the opposite property of L is not injective is L is injective. It follows that what is the opposite property of M less than or equal N? It would be M greater than or equal N. Okay? Two equivalent statements of the same theorem. These are not two theorems. Different equivalent statements of the same theorem. Now let's do the same analysis for the surjectiveness. If we take L from R3 onto R4, R3 to R4, the associated matrix is a matrix having 4 rows and 3 columns. This is the matrix. 4 times 3. There is the exchange. 4 rows times 3 columns. This matrix acts on vectors belonging to R3. That is x1, x2, x3 equal a vector belonging to R4. y1, y2, y3, y4. In the previous case, we have studied the injectiveness in relation to by applying the theorem connecting injectiveness and the kernel. We have not studied this equation directly. We have used that useful theorem. L is injective if and only if its kernel consists of the vector only. Now, for the surjectiveness, we studied the equation directly. Well, what is the conclusion? In this case, the L is not surjective. Why? Is not surjective. Why? Because what is the rank of this matrix? The definition, the recap for the surjectiveness is for any vector W, this is the vector W. This is the vector X. For any vector W, this equation, or I could write the system equation, vector equation is a tau to say linear system. Well, for this rank, the highest possible rank of this matrix is 3, because the greatest minor matrices are of order 3. Okay, the highest possible rank is 3. Then we can have rank 2, rank 1. But the highest possible rank is 3. Well, if this rank would be 3, the maximum possible, it cannot happen that for any W, this equation has always solution, has at least one solution. And is surjective if this system has always solutions, we can say in other words. But this system cannot have always solutions for any W here, because this matrix of the coefficients has its highest possible rank equal to 3. For a moment I cancel the vector on which the matrix acts. This is the matrix of the coefficient. Let's suppose of rank 3 or of rank 2. But the complete matrix, 4 times 4 for some constant, for some vector W, can always have a greater rank than the first matrix. For example, if this rank is 3, for example, this minor matrix has non-vanishing determinant, the rank is 3. But then, when I add the last column consisting of the components of W, the matrix is 4 times 4. And for some W, this matrix could have rank 4. Okay? And then the ranks are different. In this case, for this W, the rank is 4 greater than 3 of the matrix of the coefficient. Anyway, it is different from the rank of the matrix of the coefficient. And then it is a question of no solution, not at least one solution. If instead the rank would be 2, if the rank is 2, for example, all minors of order 3 have vanishing determinant. In this case, the rank is 2, for example. But if we add also the fourth column, for some W, the matrix could have, the complete matrix could have a minor of order 3 with non-vanishing determinant. For example, this minor plus this term, and then these elements and this element 1, 2, 3, 1, 2, 3, 1, 2, 3. This minor of order 3 consisting of these terms and these terms, if we extract this one, and then one element only. If here we have 1, 2, 3, 1, 2, 3, a minor of order 3. This minor of order 3 could be different, could have determinant not equal to 0. And then the rank of the first matrix is 2, because here all minors of order 3 are 0. But if we add the last column, the rank can increase, because the new column could make appear new minors not involving this column, for which here we have a minor of order 3 with a non-vanishing determinant. And then we have discovered that, from R3 into R4, we can write like here. We can write, I cancel here n less than or equal n, the first dimension, less than or equal m, gives L is not surjective. or we can say in equivalent form, we invert, we exchange test and hypothesis with the opposite properties. L is the contrary of is not injective, is not subjective. The contrary property will be L is surjective. L is surjective. L is surjective, from which we get the thesis equal to the contrary of the hypothesis. What is this hypothesis? The moment is L n less than the opposite property. The opposite property is n greater than or equal to n. Okay? These are the two equivalent statements of the same theorem obtained, proved by means of an analysis based on the Injective theorem. Now, let's consider among these two theorems, what do we want to consider? I cancel the proofs. Now, we can say I cancel, I consider. Here we have two equivalent statements. I use only one statement. I choose the second statement. And I cancel the first statement. Here I choose the second statement again. I cancel the first statement. Now the question is, if L is simultaneously injective and surjective, it follows that if L is injective, M is greater or equal to N. M greater than or equal to N. N is subjective, but L is also subjective. If L is subjective, we have N greater than or equal to N, or I write M less than. M less than towards the direction. M less than or equal to N. Less than or equal to N. But if M, this is M, if M is simultaneously greater than or equal and less than or equal to N, what is the consequence? That M is equal to N. M equal to N. Okay? M greater than or equal, M less than or equal, gives M equal N. or equivalently, let's consider, let's neglect this, and let's consider the theorem for the first property. The first property follows. We can write equivalently m not equal to n. What is the contrary of m equal n? Is m not equal to n. What is the consequence? The contrary of the hypothesis written at the base. What is the contrary of L is injective and the surjective? The contrary is, and you remember the coordination. L is not injective or L and becomes O. Or L is not surjective. And then, if the two dimensions are different, L cannot be simultaneously injective and surjective. Injective and surjective. One of the two properties does not hold if L is different to L. And then, since we want to understand the form of a linear application simultaneously injective and surjective, we have that if L is injective and surjective, the two dimensions of the two spaces must be equal, because different dimensions cannot give L simultaneously injective or L surjective. Okay, well, now we consider the same dimension. Now, the last analysis, if the dimensions are the same, the square matrix is the associated matrix is the square matrix, and A's and are the same if they are equal. Well, but what is the property of this matrix? What is the property of the matrix associated to a linear application L simultaneously injective and surjective? If L is injective, the consequence is that its kernel, the kernel of L injective, gives kernel L equal to the vector only. But a square matrix can have only the vector in the kernel. We want only this equality, not with other vectors here. And then, if the kernel consists of the vector only, the determinant of the square matrix, here I can write the determinant because the associated matrix, when the dimensions are equal, the square matrix is a square matrix. And then the determinant of A is not equal to 0. If L is injective, it follows that the kernel consists only the vector only. But if the kernel contains the vector only, this transformation with a square matrix, if the transformation transforms only the vector into in the vector, this means that the determinant is not equal to 0. Okay? This determinant is not equal to 0. But if this determinant is not equal to 0, on the other hand, we have that the concept of the surjectiveness, because for every W, this system has always one solution. If this determinant is not equal to 0, by virtue of surjectivity theorem, and then the conclusion is L is injective and surjective. This means that determinant of A is not equal to 0. Look at the beauty, at the simplicity of the conditions. If L is simultaneously injective and surjective, it follows that the determinant of the square matrix, the matrix is a square matrix because L simultaneously injective and surjective has the same dimension. And then the matrix is a square matrix for which the determinant is defined and is not equal to 0. But obviously, also the opposite theorem holds. That is, also the theorem holds. If the determinant is not equal to 0, if a linear application has the same dimensions and the square matrix has determinant not equal to 0, it follows that L is injective, but it is also surjective, and it is also surjective because if the determinant is not equal to 0, this system for any vector has always at least one solution. It is not at least because it is exactly one solution. And then the conclusion is the concept of L simultaneously injective and surjective is equivalent to say that the dimension of the two spaces are equal and that the determinant of the square matrix represented in the linear application has non-vanishing determinant. This is the characteristic of a linear application which is simultaneously injective and surjective. This concept is equivalent to saying that the matrix is a square matrix having non-vanishing determinant. Well, I stop the record.